Hi, my name is Yannick Maus, and this is joint work with Tigran Tonoyan. I will present our paper, Local Conflict Coloring Revisited, Lineal for Lists. So this is a standard distributed graph algorithms paper. So the setting is the local model. We have a communication network with vertices which represent computers, and the objective is to color this communication network, that is compute the proper vertex coloring. And the oldest result in this area is by Linial, and he showed that there exists a fast, simple, deterministic, distributed algorithm to color such a network with many colors. In this paper, we show an equivalent version of this result, but we show that there exists a fast, simple, distributed algorithm to list color with many colors. List color means that while in the standard coloring problem, each vertex can pick a color from some globally known color space. In the list color ring problem, each vertex has its private list of colors and has to choose a color from this list. So usually the objective in this area is not to just color with many colors, but to color with few colors. And I will also quickly tell you how this helps to actually color with few colors. So the setting that we have here is a standard local model. So we have this communication network, and this also serves as a problem instance. So each node represents a computer and is assigned a unique ID, and we consider deterministic algorithms in this talk. And then these vertices can communicate with each other in discrete synchronous rounds. In one round, they can perform some local computations, exchange messages with all their neighbors. And here, the local computation time and the message size are both unbounded. So the only complexity measure that we consider here is a number of rounds until each node has terminated. This won't be the model of this paper, but we use it for reference. Another model in this area is the CONGEST model, which is the same, but here the message sizes are smaller and of size order of log n bits. And the problem that we want to solve here on this communication network is the standard vertex coloring problem, or sometimes the list coloring problem. So we want to compute the proper coloring, meaning each vertex should output a color such that adjacent vertices output distinct colors. And the crux here is that at the start, a node doesn't know the topology of the network and needs to communicate with its neighbors to coordinate its actions. And as I said, usually we want to color with few colors, and few colors here in this area usually means delta plus 1 colors, where delta is the maximum degree of the graph. Note that any graph has a delta plus 1 coloring, and you can simply compute it sequentially very easy by just iterating through the vertices in an arbitrary order. So delta plus 1, this is what I consider few colors. And this old result by Linial uses roughly delta squared colors. And this is what I consider many colors. So what's known about this delta plus 1 coloring problem, vertex coloring problem? Well, first of all, we have the local model and we have results in the CONGEST model. And the first word of complexities or things that people looked at is when the complexity, the number of rounds, is expressed as a function of n, the number of nodes. And here it was a big open problem for a long time, but due to a breakthrough from stock 20 by Rosson and Ghaffari, we now have polylog n algorithm to solve this problem, even deterministically. And this is what we call efficient and very good here. And then building up on this result, we also got this in the CONGEST model. I won't talk about this regime of complexities today in this talk, but instead focus on a regime where the complexity in terms of n has to be really small, only a log star n term. Log star is a number of times you need to iterate a logarithm until you become constant. So in this world, the main factor or the main term in the complexity is this f of delta function. And here we also have algorithms in the CONGEST model, sublinear algorithm by Barenboim from POTC 15. And what I will talk about today is an algorithm with complexity roughly square root delta. This works in the local model. So I will talk about the top the bottom left corner here, local algorithm and complexity, mainly as a function of the maximum degree. So let's look a bit more detailed about the history and what's known in this area. So, and first of all, one can ask, why do we have this log star n term here and not just completely abandon any dependency on n? And this is due to a classic lower bound by Linial. In this first paper, he showed that this is necessary. You cannot avoid this log star n dependency, even if you just want to color rings and know that the topology is a ring graph, the network graph. With a constant number of colors, you need log star n rounds. And then in the same paper, he also provided an upper bound of order of log star n rounds. But this is now for order of delta squared coloring. And as I said, usually the goal here in this area is to color with few colors, namely delta plus 1, and delta squared is not few, it's very far from delta plus 1. But with a method which is called simple color reduction, it's very easy to reduce one color at a time and compute the delta plus 1 coloring after you first have computed a delta squared coloring. And then if you parallelize this, you get a delta times log delta coloring algorithm. And yeah, then in 2009, here it says JACM 14, but the conference versions appeared in 2009. Barenbaum, Elkin, and Kuhn simultaneously in 2 different papers obtained the first linear and delta round algorithm. I have another paper here from Pozzi 18, which has linear and delta runtime, mainly because this algorithm is simpler, and variations of this algorithm are also needed in our work here. And at this time, people started to conjecture maybe linear and delta is actually a lower bound. And what we showed is that at least we have a lower bound of delta to the 1/3 in a weaker model, in the set local model. But already not all of these algorithms actually work in the set local model. And if one zooms out a bit, then there are other problems. I don't want to talk about what these other problems are here now, but these are very central in this area, often referred to as the Big Four. And it turned out that for 2 of these, this conjecture of linear and delta lower bound actually turned out to be true. And we have matching linear and delta upper bounds and lower bounds now. While the state of the art for these vertex and also edge covering problem, we are very far from having these tight answers. And it turns out the conjecture is even not correct, because in 2015, Barenbaum got a sublinear and delta algorithm with a runtime of delta to the 3/4. And this was later improved by Fregnault, Heinrich, and Kozowski, who roughly got a square root delta algorithm. And now we in this paper, we improved this runtime a little bit more by also getting a roughly square root delta algorithm. So you can see the runtime improvement that we get here is only this, we get rid of this log star delta term. And I'm very sure we're not accepted for this, for this marginal gain or improvement here in the runtime, but rather for the technical contribution or the technical insights that our results give. Because we obtain this result at the bottom with very similar methods as Linial got this, this initial results. While our work is clearly inspired by Fregnault, Heinrich, and Kozowski, very much, we got a lot of inspiration from their work. Our work now simplifies a lot of the steps from their work and does an almost formal connection back to this result by Linial. So in the rest of the talk, I will first spend quite some time to actually explain this old algorithm by Linial, but from a slightly different viewpoint than it's usually done. Then I'll show how we get a list variant of this result and what I even mean by this list variant of this result. And then at the very end, I'll very quickly on one slide show you how this is helpful to actually obtain a delta plus 1 coloring. Okay, so let me begin with the first part, and revisiting Linial's result. At the very core of his result is a very simple one-round color reduction. So there you're given an M coloring and you compute the coloring with significantly fewer colors, a K coloring, and K is roughly the order of delta squared here. And then how does he obtain his main result? Well, he first considers the ID assignment that is given to the nodes as an N coloring, and then he applies this one-round color reduction, and he repeatedly applies it, and you can see there's a small dependency on the number of colors that you insert into this result, this log M. And if you repeat this and have a few additional tricks, you obtain a order of delta squared coloring after roughly log star n iterations. So today I just want to look at this very simple one-round algorithm. And how does this work? Basically, it just works as follows. Each node selects a set of candidate colors. We'll later tell you how a node does this selection, but you just select a set of candidate colors. And then you pick a color which is one of your candidate colors, but not a candidate color of your neighbors. This reads round of communication to learn the candidate colors of your neighbors. So let's look at an example. So this node with input color 11 picks a set of candidate output colors 2, 3, 7, and 9. And all the other nodes also pick some set of candidate colors. Now it gets rid of all the colors in its candidate list that are also candidates of some other neighbor. And here, color 7 remains. So the difficult part, of course, is to choose this candidate set, color set, such that you always have one color that you can pick in the end after removing candidates of your neighbors. And one way of obtaining this is by having a so-called low intersecting set family. So basically these candidate sets, and you need one for each input color, and there you already see how they're assigned. You just hard code your input color to one of these candidate sets. So you need M sets S1 to Sm, such that pairwise these sets have a small intersection. You don't need to look at the specific choice of parameters here, but pairwise they have a small intersection and each set is large. And now if you remove all the intersections with one of your neighbors and you have few intersections with each neighbor, then you have at least one color remaining if your set is large enough. And this is the whole algorithm. The difficult part here is how do you show that such a low intersecting set family exists? There are different proofs for this. One is the probabilistic method. There are constructions based on polynomials. But what I want to talk about here, because I think it has been completely unnoticed in this distributed area, even so it's super simple, and this is taught in almost every class in the area, is a very simple greedy construction to prove this. Because what you can do is you just consider the space of all subsets of this fixed size. And then you just iterate. You pick your first set and you delete all sets which conflict too much with it. And then you repeat. You pick the second set. You delete all the sets which conflict too much with it, which have a too large intersection. And a simple one-line calculation, we have it in the appendix of our paper, shows that you can continue for m steps and construct such a family with the parameters that you want to choose. So this is what Linial has done and which is taught in many courses. And a more abstract view on this algorithm is that you want to solve this problem P0. And this is the roughly orders delta squared coloring problem. And you do that by first solving this problem of assigning each node a candidate set of colors. This is the problem that you need to solve here. If you have this, everyone sends its candidate colors to its neighbors, and you can solve the original problem with one round of communication. And then this problem of assigning and giving each vertex such a candidate set, it's never actually touched in courses in detail how it's actually done. It's just shown that such a set family exists, and then you have a hard coding of input color to this candidate set. What we now have is a list coloring equivalent of this exact same result. And I can already spoil here, we don't do it in one round, but in 2 rounds. And by list coloring equivalent, I mean we solve in 2 rounds the problem where each node has some list LV, and the list has to be a certain size at least, roughly delta squared. Ignore for now all these polylog factors that are behind there. And now if we would have like to do the same approach, we would do the same, give each node just a candidate color set, but now it has to be a subset of candidate colors of its own list, because it cannot choose a color which is not in its list. And we do the same. Unfortunately, now we cannot do the same magic. We do not know how to assign these candidate sets to each node and hard code it such that each node gets a subset of its own list, while respecting that neighboring candidate lists have a small intersection and lists are small enough. So this does not work. But instead, we solve this same problem with a similar approach, but a higher order version of the same approach. So in fact, instead of just giving each node one candidate set, we give each node many candidate sets. And then you use 1 round of communication to select one candidate set. And then we solve this problem P prime 1. So let me do this a bit slower. So I will tell you later, or yeah, in the paper we show how you can select such a family of sets of candidate sets. Each vertex gets many of these candidate sets. And then in 1 round, you pick one of these sets, which is good. Good in the sense you don't have a large intersection with any of your neighbors, with a set that any of your neighbors picks. So this is like a higher order of I pick a color which none of my neighbors has as a candidate color. So you need to define a higher order conflict relation here to make this work. And then in the second round, you just do the same as Linial does. You pick a candidate color, which is not a candidate color of any of your neighbors. So these 2 rounds are the whole algorithm. The magic, of course, is in the first step. How do you select this family of sets? And how do you show that such a family of sets exists such that this whole process works? So let's look at these 2 problems here side by side. So in both, we want to solve some problem which colors with roughly delta squared colors. Lineal for list, it's a list coloring, and lineal is a standard coloring. To solve this, we want to give each vertex a set of candidate colors, such that neighboring vertices have a small intersection in their candidate sets. For linear color reduction, we can do this magically without communication, just by hard coding. For lineal for list, we do a higher order version of this whole problem by assigning each node what we call a low intersecting family of candidate sets. So each vertex gets many of these sets, and then you communicate, learn the sets of your neighbors, and pick one of the candidate sets, which is good. And here, then what we do, we show that you don't need communication to now hard code such a family of candidate sets. That works here. And I won't have a slide on the proof now, but the proof works with a similar greedy procedure. The crux here, or the difficulty here, is you have to do greedy in the right subspace of family of candidate sets. If you restrict yourself to the right subspace of these families, then you can just pick the first family, get rid of all the families that don't work with the first family, pick the next family, and so on. So in a high level way, it's very similar to this linear color reduction. So now let me tell you how our two-round algorithm here, which solves list coloring with many colors, we have this delta squared dependency here, or requirement on the list size, is helpful to actually color with few colors, with delta plus 1 colors. And for that, we first need one observation. One observation is that everything I've been telling you so far also works for bounded out degree. So just assume you have an orientation of the edges of the graph, and each vertex has at most beta outgoing edges. Now, if a vertex only erases the candidate colors of its out neighbors, then we can just replace the max degree bound delta by the max out degree bound beta in all our results. Then we also need the concept of a beta out degree partition. This is simply a partition of the vertices into p parts plus an orientation of the edges inside each part, such that the out degree inside of this orientation inside each part is at most beta. And the good thing is we also know from this nice paper from 2018 how to compute such partitions. So given a delta squared coloring, which we can, for example, compute with Linial's coloring algorithm, one can compute the beta out degree partition into roughly delta over beta parts. And the runtime is linear in the number of parts. So this is everything that we need to present our main result, our main algorithm. Here I stated the result for degree plus 1 list coloring in roughly square root delta time plus log star n. But I will only talk about delta plus 1 coloring now. So the algorithm works as follows, and you almost have the whole algorithm on this one slide. You first compute an order of delta squared coloring, for example, with Linial's algorithm. Then you compute a beta out degree orientation for the right choice of beta. And now you iterate through the parts, and when you're at some part, you color some of the vertices of the part and some remain uncolored. And you do it, what you need to do there in one part is to actually solve a list coloring problem, because you never want to revoke any color choice, and some of your neighbors might be in previously processed parts, so they might already have a color. So you cannot take their color and need to erase these colors from your list of available colors. So actually what you need to solve in one part here is the list coloring problem. And now you simply have colored these vertices in VI, which satisfy the list size requirement of our two-round lineal for list algorithm, meaning its list size is at least this beta squared times this polylogs. What do we gain through this? We gain that everyone who is not colored here has a small list. And due to the choice of parameters, it has a list of size at most delta over 2. And how can you get a small list? Only if you erase some of the initially delta plus 1 available colors. And this means you only erase one if you have a color neighbor, if one of your neighbors gets a color. This means that your uncolored degree is also at most delta over 2. So one iteration of this decreases your uncolored degree by a factor 2. And then we just recurse. And the runtime is dominated by the first iteration. For technical reasons, we need to do a cleanup phase at the very end and cannot recurse until delta is very small. But this is essentially the whole algorithm, this part and our two-round lineal for lists. And if you want to know more about how this relates to other results, or actually how this relates to the techniques used in computing this beta out degree orientation, I recommend to watch my longer ATCA talk, where I talk a bit about this. I think there's a lot more to say about this algorithm, but I don't have time in this talk. So either check out the paper or talk to me, or both. Thanks a lot.